Hello everyone, we are Group 10 and for our weekly presentation we'll be talking about biometric verification systems using iris image processing. So just to give an outline, any biometric system acquires features from a particular individual and this is compared with features of other individuals in the database. Iris recognition is fast, reliable, and it's quite accurate when it comes to biometric systems. Now, when it comes to iris recognition, localization of the boundaries of the iris in any given eye image is considered to be the most important step. So, there are several algorithms to segment the iris. And in this particular presentation, we'll be talking about the Dogman's algorithm. It's one of the segmentation methods that's used in several commercial biometric systems. It mainly focuses upon image segmentation and feature extraction. Now, in this presentation, we talk about this algorithm which achieves best performance in terms of accuracy and time. Now the algorithm is tested on the UOIT version 1 database, and the dataset includes 15 individuals from both right and left eyes, which resulted in 45 classes in total. And the algorithm has an overall accuracy rate of 95% and it has excellent performance. Now one might ask, why iris recognition? So the first thing that comes to mind is speed and accuracy. So once implemented, iris recognition is one of the fastest biometric matching modalities in the market. It can handle very large populations with very good speed, and it's one of the most accurate. It has very low rates, almost lowest rates of false acceptance and false rejection rates. The next one is that it's quite impossible to forge, which means that it's nearly impossible to spoof or forge with any given current technology. Hence said, it's deployed around the world with no incidence of breaches using the iris recognition for any kind of security purpose. So because of this accuracy, it very well protects against any potential fraud. The next reason is because of the stability. The iris is very well protected by the eyelid, the aqueous humor, the cornea, so it does not degrade with age. And the result of injury is very less common than any other biometric recognition systems or modalities. Again, the next very important advantage is the flexibility. Because the cameras use infrared light, the scanners can be used in almost any setting, including dark. And the last and quite important advantage is that it's contactless. Given the current situation, iris recognition does not require any physical contact with the sensor, which thereby makes it more hygienic. It's very less intrusive than any other modality like fingerprints or any other biometrics that require touch. Now in any given iris recognition algorithm, these are the following steps that are involved. These are generic steps. So it all first begins with the iris database. Any analysis of image processing mainly depends upon the quality of the image. A good quality image can widely increase the accuracy of iris recognition. Now, there are different kinds of iris datasets that were used by researchers, and there were several methods used. In this presentation, we'll mainly focus upon the UOIT database. Now, the iris image datasets consist of data that's captured in the visible wavelength or at a distance and on the move. The next stage is pre-processing. It's a quite important procedure in iris acknowledgement. and it decides the achievement of the iris, including the extraction and acknowledgement. So basically the pre-processing consists of two stages. First one is the image resizing, and the second one is the image localization. So when it comes to image resizing, it means the image of the iris is resized from the smallest to largest or largest to smallest, somewhat compatible to the single database. Now resizing the image can drastically decrease the processing time because of the decreasing size of the image. The next part of this process is the image localization. Sometimes iris images can additionally capture other parts of the eye, such as the eyelash or the eyelid. So because of this, the texture of the iris gets distorted. So the artifact must dispose of all the unwanted features for an effective pre-processing stage. The next step, which is segmentation, basically detects every boundary of the iris and the pupil automatically in any given eye image. Now, after the segmentation process, the next stage is to change the part of the iris to a predefined dimensional pattern. So basically, the regions of the iris are mapped to polar coordinates. So when it comes to Dogman's algorithm, this process is achieved using the Dogman's rubber sheet model. And the last stage is the feature extraction. So in any given iris image, different features can be extracted, such as textural features which define pattern, spectral features like color and gradient, and geometric features like shape, size, edge, and so on.
Thanks, Marathi. Let's have detailed implementation process of how the Dogman algorithm captures the iris images of the human and comparing with the iris template database. The first acquisition of the iris image of the human, and then localizing the iris image to speed up the performance of the image recognition, then projecting into the segmentation process to define the boundaries of the iris and pupil. The sample is then refined for the extracting the discriminating features without any noise, and then converting the iris segmented data into the polar coordinates. Then using some mathematical functions such as 2D Caber wavelets and demodulation code to extract the features and turn them into the biometric template. So the biometric template is then normalized and converted into the iris code, which finally produces the binary code, then compared with the pre-stored iris templates from the database. So here, as part of the verification mode, like 1-to-1, the system compares the person identity and captured biometric data with a template stored in the database. As part of the identification mode, the system identifies the person by searching the templates of all users in the database for a match. Yeah, this is called one-to-many. So here, let's have the comprehensive view of the primary part of the implementation called the localizing and segmenting the iris image. The first iris image was captured in the monochrome CCD camera, which produced around 7100 504 pixelated iris image. So as part of this segmentation, it is necessary to localize precisely the inner and outer boundaries of the iris to detect and exclude eyelets if they intrude. So these detection operations are accomplished by intro differential operations like operators passing the size and location of the iris and pupil coordinates, and this function generates the boundaries. Yes, this proposed method works on the eye captured under the unconstrained environment such as non-uniform lighting conditions and illuminations. So in this image you can see the eye captured with the reflections at some distance of 50 meters, and these specular reflections are removed by using morphological operator as shown in this right image. Yeah. So one of the challenge in finding the boundaries is the low contrast or low lightning eye images. So the document process helps to overcome these limitations using the proposed integral formula which I captured in this slide. So to reduce the false acceptance rate and false rejection rate, the pupil and iris localization should be accurately detected. That's the goal of the stage. So once the iris and pupillary boundaries are detected, during the normalization, the irises are converted to standard size dimensions like predefined and fixed size dimensions, and then encode it as an iris template for matching between the iris templates. Here the goal of this step is to convert every point inside the iris region should be converted to the pair of polar coordinates. Yeah, we perfectly define the iris region and pupil region, and then this whole part is considered in Cartesian format. So typically the process is conversion from the Cartesian to non-concentric polar representation. So this converted model is called homogeneous rubber sheet model or the Dugman rubber sheet model, where every point inside the iris region will be converted into the polar coordinates like r comma theta. So where r ranges from 0 1 and which pointing waves forms inside the iris regions, and theta ranges from 0 comma 2 pi. So which is shown here. Yeah, from the whole iris region, the iris region from 45 to 315 and 315 to 225 degree are considered for the iris segmentation, because the remaining part like this will avoid the eyelashes and eyelets shadows on the iris, so this will be removed, and only the regions between these degrees will be considered for the segmentations. So this Dugman derived formula calculating the polar coordinates from the pupil and iris coordinates. So as part of the feature extraction, we can achieve to have a high entropy and encode the iris pattern to iris code. So after the calculation of the iris polar coordinates and then projecting these coordinates onto these wavelets called 2D Caber wavelets, which have complex exponential time cosiines. So basically the Caber wavelets filters are popularly used in many applications of image processing such as extraction of edges, textures, analysis and object recognition. So to minimize the deviation and uncertainty information, these Caber wavelets projections are playing the primary role in the Dugman algorithm. So we are projecting iris patterns into all the different patches onto these wavelets to set the real and imaginary parts of the bits. So as everyone knows that all the 1 bit space towards of the waves and all the 0 bit spaces towards the down in the waves. So which divides 4 quadrant concept. So all the quadrants identifying the iris patch precisely. So after all the different patches of the iris position analysis, it generates a pair of bits. Here you can see the actual 4 iris code of the 4 actual eyes. So these black and white patterns are combinations of the random texture of the iris pattern, and all together we get 2048 bits. That 512 bytes iris code looks like this. So as part of the pattern matching, finding the Hamming distance between two iris patterns gives us knowledge of the number of bits that are the same in 2 bits patterns. So upon using Hamming distance, we can decide whether two patterns were generated from the same iris or different irises. Here the simple Boolean operations of XOR and AND between the two iris codes to find the Hamming distance. So let's have an example of comparing the iris code. See here, the code A and code B are two 16-bits iris code from the different eyes. So XORing these code A and code B produces 16-bit chunks of binary. And then excluding unwanted non-iris codes such as eyelash and eyelids produces again 16-bit binary. Then find common bits between these two results produces again 16-bit binary. If you find the total bit difference between this iris and non-iris code is 8 bits, which says agreed bits are 4 and non-agreed bits are 4, then Hamming distance is 4 out of 8 is like 0.5, says two iris codes are not related. So if it is an exact match, then two iris codes should be tallied means equal to 0. Yeah. So in terms of performance, since it is single line Boolean operation to compare the irises, we can achieve the rapid comparison and greater computational power with a 32-bit machine clocked at 300 MHz CPU to compare iris samples scaled at 0 to 4 billion store template. As you can see, the results of the Dugman iris recognition process tested with 40 to 58 different iris samples. The agreed proportion of the Hamming distance between two different irises from these samples is 0.5, which is calculated from 9.1 million comparisons. Yeah, These data are acquired from the licenses of these algorithms in the countries UK, USA, Japan, and Korea. So, what are all the constraints followed during the 9.1 million comparisons of 40 to 58 iris samples? So, these are constraints like no images are from the duplicate or same eyes, the not counting pair two times, and none of the images are by themselves compared by themselves. So all the images are different and unique. So this searching machine can obtain 1 million comparisons in 1.7 seconds on the server clocked at 2 gigahertz. This remembering is one of the most powerful biometric comparison methods among others. Yeah. As you can see here, the most complex texture and around the pupil area is called entropy, which gives the most complex iris code. So where there is much entropy, then you won't get collision among the different iris code. So entropy provides more resistance against the colliding between two different people's iris codes. So chances of the same bits will be indefinitesimal, means a false match rate of almost zero. Yeah. See here I would like to share one real-time application. So due to the high entropy rates of the iris, the government of India launched a program called the Unique Identification of Authority of India. So far they have enrolled 9 to 8 million citizens iris samples for identification as of 2015. Yeah, but right now they almost done it, I guess. So which is almost 20 times greater than the FPI database. And also the Indian government uses this iris code for their Aadhaar ID, which aids people to not carry paper ID and fast identification of the person in the highest population country in the world. So the common features so far encountered in enrolling of the iris biometrics, the common failures encountered in iris biometrics, where the lag in getting strong entropy due to an untreated medical conditions like untreated ocular diseases, as listed here, like SCAD, opaque cornea and collabo and cataract. So if the persons are having these kind of diseases, it's very difficult for to register the iris of the person. Yeah, and the vulnerabilities and challenges and solution will going to be carried forward by the Toshi. Thank you.
Thank you, Nirosh. Hi class. So the I'm going to continue with the biometric security challenges and possible solutions. So the biometrics are typically noisy and reading very even for the same object. So the match are approximate. So providing the security protection to the iris biometric system is a crucial aspect for the authentication system, but it's surprisingly difficult to do in a way that is easy to deploy and use. So one of the common vulnerability of the iris biometrics is the weakness of binary matching patterns. So the binary authentication decision in the matching steps are fragile and it can be skipped or even flipped by accidental error. So the matching requires the reference template to be readily available during the authentication and creating opportunity for an attacker to steal the templates and also is enable the further attacks going forward. So the binary nature of the decision is also implies that the system must have access to all the resource that's probably a authenticated user might need. So that is forcing a violation of the principle for the least privileges. So these inherent weaknesses become especially apparent in the settings where it's not clear who can be trusted to perform and the matching granted access, right? So as you can see in the general iris binary authentications and the authorization system in this image, the first is the authentication data such as password or a biometric collection from the user. It transfer into the approximate canonical forms or its templates. The next is it will get the template is matched against the store reference templates, and if the match is successful, then the authorization framework grant the users to access the approximate resource. So the three major vulnerability component on this approach are highlighted in a red color triangle. So um, the first one is matching, which is the fragile binary decision, and the second one is store the template, and the third one is authorization framework. So the biometric, the possible solution for the second one is the crypto system paradigms. So the alternate approach is to drive a cryptographic key from the biometrics. So this approach is originated with the work on a fuzzy commitment and also the fuzzy wallet. So these ideas were formalized in a cryptographic object known as the fuzzy extractor, that is reliably produce a uniform key from the noise. The source of entropy, which is the fuzzy extractors. So this approach has also been investigated under the name of biometric crypto system and biometric key generations. So the second algorithm reproduce and or use the authentication time, taking nearby entropy value and also the public values to produce a second key. So the figure shown in a full authentication system implemented using cryptography, authentication and authorization concept, which will eliminate the weakness of the binary. So the matching paradigm vulnerability. Here are the authentication data is collected from the user and transferred into the canonical form or the template that is used. But instead of matching these accurate templates against the store reference templates, uh, so the accurate template is used to generate the cryptographic key so that the key can be used to obtain the access to the resource Viva cryptography access. So the vulnerability highlighted in the figure 1 are no longer present by following the key exchange. So the future direction of iris biometrics has considered several things in terms of performance, accuracy, and production, and a new technology adaptation. So an iris recognition system was introduced using CASIA version 1 or VG16. The neural model is contain a grayscale of eye image to the investigated to the artificial neural network to recognize the process. So to identify the iris as an individual artificial neural network is used in automated segmentation algorithms. So the artificial neural network technique is also used for classifying the features to related person, and also the system perform evaluate by calculating the validation accuracy of the random number of test images. So in the real world situation, iris recognition system must grip and spot all the type of spoofing attack. So there is the prerequisite to the graving framework that sends all the type of prevalent spoofing attacks. So the prevailing there is no data set available, so in which include all the probable and identified images of the attacks. So there is the data sheet that created hotly discussed for the verification method. So the concern can be handled by creating a standard format to the preset of IRI data sets, and it can be prevent from these attacks. So these are the reference that we use for our presentation. Thank you for listening, and have a good evening, guys.